So, you're all doing well. Come back to another session. Today, last time we looked at Newton's laws. It was chapter 2 of Newton's laws with certain tips. Today we're gonna be looking at electric currents. We're gonna be looking at the physical science paper for 2022 November. So we'll go through some questions, and while going through the questions, we'll explain a few things, explain a few concepts, and so on. So yeah, before we start, heading right in, we'll start by explaining a few things about electric circuits, right? And we're gonna start with a simple circuit. No. So let's say we have a circuit, and on a circuit we have a resistor, and with a resistor and an ammeter, right? So let's say we have a circuit like this, and we are told that there's 8 volts coming out of this circuit. We are told that we have a resistance of 3 ohms, let's say, for example. Now we know the formula for Ohm's laws is R is equals to V over I, which our I, that's our ammeter. That's our ammeter, so that's our current, and it's measured in ampere. Our R, that's our resistance, and it's measured in ohms, And now the V, that's the voltage or the potential difference, and it's measured in volts. So this is all basic. This is all the basics of electric circuits. Now, if we ask a question with this simple circuit, if we ask a question, what is the because we're given the resistance, we're given the voltage. If we ask what is the current, then we'll just simply substitute and say the current is equals to the resistance divide, sorry, not resistance, so it will just be the voltage divided by the resistance, and then in which it will have 8 and we'll have 3, and then the answer will be our current. Now this is for simple circuit. You probably don't get this in grade 11, 10, I mean grade 11, 12, and so on. So now, but what I need to explain is this, right? We'll start with looking at the formula I is equals to V I. Looking at the formula, we'll start with our current, which is said it's measured in amperes, right? Our current, which is measured in amperes, has certain things that we should know about it. For one, it's always connected in series. To measure the current here, you must connect it in series. So for you to measure current, you must connect it in series rather than parallel. You won't find an electric circuit where you say, let's say you have a resistance, right? And let's say I want to measure, let me put it here. Okay, so let's say I have a resistance, I have a resistor here, and I want to measure the current going through this resistor. And I want to measure the current going through this resistor. If I want to measure the current going through this resistor, there's no way I'm going to place my ammeter on parallel. There's no way I'm going to place it like this. If you place an ammeter in parallel like this, it won't measure your current. So this is correct form. So if you want to measure current, you place your ammeter in series, not in parallel. So meaning, if I want to measure the current going through this resistor, I will place my ammeter here or anywhere here. That's still fine, but the most important thing should be in series. Now, opposite for the voltage. If I want to measure the voltage across a resistor, I do the opposite of what I do with an ammeter. So I'll place my my voltmeter in parallel form like this. I do not place it in series. There's no way I'm gonna place my voltage like this and saying I'm measuring the voltage across the resistor. There's no way I'm gonna put my voltage here and say I'm measuring the voltage across this resistor. That's not how it's done. Now, while on that, we'll explain in terms of, now let's go to resistors. Now, this, if they ask me for total resistance in a circuit, it's the resistance when you combine the resistance of all the resistors in your circuit. So in this case, we only have one resistor. So if they wanted our total resistance, we'll only have the resistance. We'll only have this one. So we only have this resistance. So this resistance will equal to the total resistance of the circuit. But if I decide to add another resistor, here like this, let's say we had 3 ohms and we have 2 ohms. If I decide to add another resistor like this and they ask me for the total resistance in the circuit, the total resistance in the circuit is no longer 3 ohms, but we have 2 resistors in the circuit. So the total resistance is the resistance of the total circuit, total resistances in the circuit. So that means my total resistance, because these resistors are in series, we just add them. So my total resistance will equal to 3 ohms plus the 2 ohms. So which means it will be equal to 3 plus 2, which will equal to 5 ohms. So in this circuit, my resistance will equal to 5 ohms. Right? Now, the same scenario, but this time we won't put let's just extend it and do it parallel. So this is parallel. So in terms of parallel, if I still have, let's say, 3 ohms and 4 ohms, right? Now I have this scenario. Now my resistors are no longer in series but in parallel, and in this case it won't be the same. My total resistance will be equal to all the resistance in the circuit, but in terms of adding in series and in parallel, it's not the same. So for in series, my R total is equals to R1 plus R2 plus R3 and so on, depending on how many resistors you have. But in parallel, the R total in parallel is equals to 1 over R1 plus 1 over R2 plus 1 over R3 and so on. You get it? Now, in parallel, there are 2 ways you can calculate your resistors. You can do it this way, or you can do it this way. R total is equals to R1 times R2 over R1 plus R2. But this method only works with 2 resistors, so you can't add more. It works with 2 resistors. You don't add more than 2. You don't do it with more than 2 resistors. So don't come and say time is R3 plus R3. So it works with 2 resistors. So if it's more than 2 resistors you wanna calculate, it's better to opt for to go with this formula. Okay. Now let's dive into the questions we have today. Okay. Okay. They say the circuit diagram below shows 4 resistors connected to a battery of EMF and internal resistance. The resistance of the ammeter and the connecting wires are negligible, while the voltmeters have very high resistance. Okay. So then we are told that the circuit below shows 4 resistors, and as you can see, we have the 3 ohm resistor, we have the 1 ohm resistor, we have the 2 ohm resistor, we have the 4 ohm resistor. Now looking at our resistors, we can see that the 3 ohm and then 2 ohm resistor are in series, not parallel. The 2 ohm resistor and the 3 ohm resistor are in series, but the 3 ohm and the 2 ohm resistor are in parallel with the 1 ohm resistor. So where do you look for whether the resistors are in series or in parallel? You look at where the current splits. So let's say here the current was moving this direction. It moves. When it arrives here, if this circuit, obviously if switch S is still closed, the current will split. So if it splits, the other one will go this way, the other one will go that way. So if that happens, then it means the reason why we say these ones are in series is because the same current that moves past the 3 ohm resistor will be the same current that passes through the 2 ohms resistor. But it won't be the same current that passes through the 1 ohm resistor. So that is why we say the 3 ohm plus the 2 ohm resistor, they're in parallel with the 1 ohm resistor. But the 3 ohm and the 2 ohm resistor are in series. They are not in parallel. Now looking at the 4 ohm resistor, the 4 ohm resistor is in series. So it's connected in series. So it's in series all the way. So because as you can see, after here the current will combine. If it combines and goes back, it passes here. So that means we can already see that the current that passes through the 4 ohm resistor, it's the total current of the circuit. Here the current splits, so it shares. We don't know how much passes here, how much passes here. But you know the same that passes here, the same that passes here. But when it comes to the 4 ohm resistor, we know that the current that passes to the 4 ohm resistor, that's the total current. That's the total, which means total current here we have, as you can see, 3.5 ammeter. So that we know that the current that passes to the 4 ohm resistor, it's still 3.5 ohm. 3.5. Now looking here, we have a voltmeter, or we have a switch. So the switch, it's closed. As you can see, it's closed. So we have a switch and we have an ammeter, 3.5. So as you can see, it's connected in series, and this is the total current. If it was placed, if the ammeter was placed here or anywhere here, we would say it's the current for this, the 3 ohm and the 2 ohm for the 1 ohm. But because it's placed here, this is the current for the total circuit. And looking at the volt, we have voltmeter 1, we have voltmeter 2. If you look at voltmeter 1 is measuring the voltage across the battery. So that means it's measuring the external voltage. But here, because they said you have an internal resistance, that means we already know that, this V1 won't necessarily be the total, total voltage, because there will be an internal. So no, I mean the total, what I mean to say is that the the resistance here, again, the last we said it's all the resistance across the resistance in the circuit equal to the total resistance. So in this case, the 4 ohm, 1 ohm, 2 ohm, and 3 ohm won't be the total resistance in the circuit, because we still have the internal resistance. So it won't be the total resistance, but it will be the external resistance. But in terms of the total resistance of the circuit, we still need to include the internal resistance of the internal resistance that we have. So V1 is measuring the voltage across the battery, and V2 is measuring the voltage. As you can see where V2 is connected. If you look at V2, it's connected in parallel with the 3 ohm and the 2 ohm resistor. So as you can see, V2 is measuring the voltage in the 3 ohm resistor and in the 2 ohms resistor. Yeah. Okay. So now we dive into the questions. I have 8.1. Say state Ohm's law in words. That one you have definition, you can read it, and but in terms, you know that the potential difference across a conductor is directly proportional to the current in that conductor at a constant temperature. That's definition for Ohm's law. Now they tell us that switches is closed. 8.2, switches is closed. And 8.2, they say the reading on the ammeter is 3.5, as we can see as well that it is 3.5. Now they say calculate the total external resistance of the circuit. Remember what I explained before? I said the 1 ohm, 3 ohm, 2 ohm, 4 ohm resistor won't necessarily be the total resistance. It will be the total external resistance, just not the total resistance of the circuit. It will be the total external. You should remember that external, because we have an internal resistance. That's because we have an internal resistance. Get that? If we didn't have an internal resistance, the 4 ohm, 2 ohm, 1 ohm, and 3 ohm will be the total resistance of the circuit. Now, V1 is measuring the EMF, which is the voltage across the battery. Now, question 8.2.1 says calculate the total external resistance of the circuit. Now, as I explained, external. So that means what they're asking us is to calculate, what they're simply asking us is to calculate the resistance across the four resistors. So the 3 ohm, the 2 ohm, the 1 ohm, and the 4 ohm. Okay, I'm just gonna redraw this. What circuit we have here? We have an ammeter. We have a battery with an internal resistance, and we have the last resistance here. Okay, so now this is the battery we have. Here we have 3 ohms, we have 2 ohms, we have 4 ohms, we have 1 ohm, and here we have R. We're not told what's the resistance here, but we have R, and also what we have, it's a voltmeter. So this is V1, and it's here, so that's V2. So let's just do this, just to separate each and every one of the components. So that will be our ammeter. Yeah, I think now each and every one of them is separate. Okay, so now the question they ask us to calculate the total external resistance. Now let's start with the ones in parallel. Now we said the 3 ohm and the 2 ohm resistor are not in parallel because they are using the same current. They're in series, but the 1 ohm it's in parallel with the 3 ohm and the 2 ohm. That's because they're not sharing the same current. So let's start with what we know. Okay, so we'll say this one's, which means R series, it's in series, will equal to the 3 ohm resistor plus the 2 ohm resistor, which will get total resistance of 5 ohm resistor. Right? So now after we get the 5 ohm resistor, this is the same as saying now we can even write our component like this. we can now even say, let's draw a line here. We can now even see we have something like this, and this is 5 ohms. So basically we can see that we can even connect this into, like, after we calculate total, so it's basically combining, say it's the same resistance in parallel with this one, and total is 5 ohms. Now, okay, so after we do that, we calculate it. So now we have to calculate the R parallel. So the R parallel will be equal to the 5 ohm that we calculated times the 1 over there, 5 plus 1. Remember I showed you this formula, or you can use the 1 over R parallel is equals to 1 over R1, 1 over R2, or you can use this one, but this one only works when it's 2. So 5 times 1, that is 5. 5 plus 1, that is 6. So let's pull up our calculator and then say 5 divided by 6. So we get 0, 0.833, let's do it to decimal place, ohms. Right, we still measuring so resistance. So now that we know that our R parallel is equals to 0, 0.833 ohms, we just will take it to this 2 decimal place in the final answer. For now, let's keep it at 3 decimal place. So now that you've calculated that, you know that this is not the final answer, because this is only for the 3. This is only the resistance for 3 ohm, 2 ohm, and 1 ohm. So we still need to calculate the one for 4. So now if we check, we said now the 3 ohm and the 1 ohm and the 2 ohm, after we calculate the resistors in parallel, we can see as you said, the 4 ohm resistor is connected in series, not parallel. So that means the R total will be the total of R parallel plus the one in series, which means we'll have 0, 0.833 plus R series, which is 4, and we'll calculate. If you put that in a calculator, let's hoping this will be 4 plus 0, 0.833. Then we'll get 4, 8. You can do it to 2 decimal place, 4,83 ohms. So this will be our final answer. This will be our final answer for this question. Okay, I think we're satisfied with that. So now let's move on to the next question. It says calculate the reading on voltmeter 1. Now, as we said, guys, the voltmeter, the V1, that's the EMF that's across the battery. So that's the total energy that the battery supplies. So that's the EMF of the circuit. So now there's this formula that we know. I think it's EMF is equals to, if I'm not mistaken, total current plus the times the resistance plus the internal resistance. Now we would use that formula. Hope I'm still. Oh, there's a formula. Can't forget for I'll double check. But in this case, we can't use this formula because we do not have what is it? We do not have the internal resistance. We don't have the value for internal resistance. But what we do have, we have the external resistance. We have the external resistance, which is the external resistance that we just calculated. We have the total current as well. So already that gives us an advantage, because we have the external. It is not because the resistance. Remember, the internal resistance is in the bed, so it's the resistance in the bed. Now we have the external resistance that we just calculated, and we have the total current in the circuit. So we are able to calculate the total, the value of V1. So our formula, that's R is equals to V over I. So that means we're gonna calculate voltage. So that means our voltage will be resistance multiplied by our current. So our resistance, the one in the total external resistance that we got was 4,8. No. Yeah, 4,83 multiplied by our current, which is 3,5. So formula, it's R is equals to V times I, and then V is equals to R times voltage is equals to R times I, because we cross multiply. Now we either put this into a calculator. We have our 4,83 multiplied by 3,5. Then we get 16,91 volts. So this will be our total, the voltage across the V1, across the battery. That will be the voltage across the battery. That will also equal to the EMF. No, not the EMF. That will be the voltage across the battery. Yes, that's, yeah, it's equal to the EMF. Okay, so we move on to the next question. Now it says, this is not a, you can do it with calculation, but mostly it just requires knowledge. So 8.2.2 says, how does the reading on the voltmeter V2 compare to the reading on voltmeter V1? Choose from smaller than, equal to, or greater than. So this you can calculate as well, but most of the time questions like this just require certain bit of knowledge. So it's just knowledge. So now, what do you think? Let's look at V1 and let's look at V2 for a second. Think about it. The V1, it's measuring the voltage across the battery. So the battery, this is our power supply, so it's measuring the voltage across it. Now when you look at the V2, it's measuring the voltage across the 3 ohm and the 2 ohm resistor. It means we haven't considered the voltage across the 4 ohm resistor. We've only considered this on V2 only measures 3 ohm and 2 ohm. We haven't considered the one across 4 ohm resistor. So already you can see that it means that's not the it's not measuring the real total voltage, it's measuring a shared voltage. So already it means we can see if this one is if V1 is measuring across a battery, then that has to be the one that the battery is supplying. So that means that has to be the bigger. That has to be the biggest. But if you look at the one across a resistor, it means that's the one that's across that resistor, not necessarily across all the other resistors. So already that means we can see that definitely V1 is definitely gonna be bigger than V2. The question says, how does the reading on voltmeter V2 compare to the reading on voltmeter 1? Choose from smaller than, equal to, or greater than. Then our answer will be smaller than. Elena concludes that the EMF of the battery is equal to the reading on voltmeter V1. Define the term EMF. Now the term EMF is the maximum, so maximum energy supplied by the battery per unit charge. Now is the Elena conclusion correct? Choose from yes, no. Now it says oh yeah, so this comes to what I was saying. So V1, remember when we calculated V1, we calculated the voltage. We calculated using what? We calculated using what is it? We calculated using the total current, but also the external current, the external resistance. Right? Not necessarily. Remember, I told you this that we didn't necessarily consider the internal resistance. We didn't calculate it because we don't have a value for it. We calculated the V1 using the external resistance. And I remember I said the external resistance, that's the external resistance, but not necessarily the total resistance, because the battery itself has total resistance in it. So which means V1 cannot really be the EMF because there's an internal resistance that we didn't consider. Oh, this is the formula I think I showed you. I said the EMF is equals to the total current multiplied by resistance, which is the total external resistance, plus the internal resistance. So already you can see if the EMF is equals to this, and we only use the current, we only use the current and the resistance. It means already this is not the EMF because we didn't use the internal resistance. We didn't consider the amount, the internal resistance. We didn't use it to calculate the total voltage. So that means this is not the EMF. This is not the maximum that the battery is supplying. Yes, it's the voltage. So it's also like external voltage if we have that, but it's not necessarily the EMF, because the EMF is the total that the battery supplies. Now this V1 is basically the one across the battery that goes into, but it's not the EMF because the battery inside remember the internal resistance, it's inside the battery. So it means if, let's say, you might find that our total voltage was the one across V1 was equals to 16.91 volts. Now if it was 16.91 volts, you might find that so let me put this like this. So you might find that, oh sorry, this is the formula I was showing you. I find that maybe the total resistance of this circuit, we're just estimating, maybe it's 18 volts, and the 1,91, so that will be the 9,09 voltage was lost, and then it was lost in the internal resistance. So the internal resistance took it, and what we got, what came out of it was the 16,91. That's the one we have across the circuit, but that's not the EMF, because the EMF, you define EMF first. EMF, it said the maximum supplied by the battery per coulomb charge. So that means that's the maximum energy, maximum voltage supplied by the battery. Now, the battery itself it's not necessarily 6,91 volts. It might be 18 volts, but because of the internal resistance, we don't get the total voltage that goes out. We will get, what we're getting is 16,91. Might find that there will be 1 commas. I'm not saying this is 18 volts, just estimating. I'm just trying to give you an example and show you how it works. Find this amount is lost in there, because if we had the internal resistance, we'd be able to easily find the EMF. If we had the value of internal resistance, we'll be easily able to find the EMF. But you also remember what they asked us. They asked us for the total external resistance, because they knew that there were internal resistance, so they asked for the external resistance. It means the external resistance across the circuit, but there was an internal resistance. So the V1 is measuring also, the V1 also is externally, so it's measuring the one supplied by the battery, but that goes out, which means externally as well. So the V1 that we got, it is the voltage, but it's not the EMF. It's not the, we need to get this. The EMF is the total power supplied by the battery. So it means the total supply. Now, if you didn't have, if they didn't tell us about the internal resistance, or we didn't even consider it, and they just ask us the V1, is it the total? We'll say V1, yes, V1 is the total supplied by the battery. But here we have internal resistance about it, so V1 cannot be the total supplied by the battery. So I hope we got that. So we just explained. They say give reasons for your answer. In question 8.3.2, we just gave reasons for that. It said it can't. So reason will be there's an internal resistance. So some energy, is used to overcome the internal resistance. Some energy, some voltage is used to overcome the internal resistance, or for being deployed in the circuit. So it can be the total. Oh, now we still are going. I think this should be second last question. Okay. Now they say switch S is now removed and replaced by voltmeter V2. As shown in the circuit. Interesting. So they say, how will each of the following change? How will each of the following change? Switch S is now replaced by voltmeter V2, showing the circuit. So okay, switch S that we had here, if we go back, we had switch S here that was closed, and now they replaced it with the voltmeter V2, and V2 last time it was here, now they've put it there. Okay, let's see how will each of the following change. Choose from increase, decrease, or remain the same. So it's also just asking us questions. So this most probably mostly require general knowledge more than calculations, because once you know what happens in a circuit when voltage, maybe when voltage is increased, when resistance is increased or decreased, what happens to the current, all those things. So it's general knowledge. Once you know all those things, these questions, you're able to answer them correctly. So it's basically just mostly just general knowledge as to, you must know what happens in a circuit when certain things changes. What happens when the switch is open? What happens when it closes? What happens when it opens? So things like that. So it's important to know your theory. Now they say choose from increase, decrease, or remains the same. So the first question is the power dissipated by the 4 ohms resistor. So I'm just looking for the formula sheet. Now let's start. This we can determine also by writing. Let's write the formula for power. We have power is equals to, let's find one with resistance on it. So that means I squared times resistance. This formula, you have it on your formula sheet. So we have this. Let's calculate it before everything changed. This is the 4 ohm resistor, right? And we'll have our total resistance, which is 3,5 squared, and our resistance, that's 4 ohms. So our power, calculate out. So that will be 3,5 squared. Oh no, not plus, multiply by 4. We'll get 49 watts. So that's our power before everything changed, before they decided to change their things. So that's now we come into the question. They say the power dissipated by the 4 ohm resistor. How will it change? How will it change it? What will happen to it? Okay. Okay. So now, because there's a voltmeter here, first thing, because there's a voltmeter here. But again, you remember what you said about voltmeter and ammeter. Voltmeter is, you only measure voltage when you connect a voltmeter across parallel like this, or like V1 is connected and V2 here in this circuit, and ammeter is connected in series. But once you connect a voltmeter here, it doesn't work. So that means we already know that current won't move here. Current won't pass through here. So current won't pass through here. So that means we'll have, okay, so current won't pass through here. So we'll have, now if that happens, if it goes through here instead, because here it won't pass because of this voltmeter, now it means our resistance will increase, right? Our resistance, total resistance here, but this is the total external resistance of the circuit will increase. So let's look at our R is equals to V over I. Okay, let's look at what I'm trying to say. We use this formula, right? So if now look at what happens. If our resistance increases, if the total resistance, external resistance of the circuit increases, because remember our external voltage that we found in V1 was 16,91, I think, yeah, volts. So if it happens that the resistance increases, if the resistance, okay, going to change color. If the resistance goes up, we can already see what will happen to our current. Once we have more resistance, we have less current. So that means if we have less current, look at this power, look at what will happen to. Now we have 3,5 here, right? We have 3,5. Let's say we do not have 3,5 here. Let's take this 3,5 out, and it's decreased. So let's put it to 2,5, and watch what will happen to our field. So let's delete this one and say 2. Check what happens to our power. We now have 25 watts. So you can see what happens. You can see what happens to our power already. Our power goes down. Why? Because if that happens, that means the 1 ohm resistor will no longer work. That means we only have resistors in series, not in parallel. When having resistors in parallel, all the resistors will be in series. And if all the resistors are in series, the resistance increases. And if that happens, if the resistance increases like that, that means our current will definitely go down. As you can see in this formula, resistance is definitely proportional to current. So when the other one goes up, the other one goes down, and the other one goes left, the other one goes right. So you can see that. So now to answer the question, so how that means the power dissipated by the 4 ohm resistor, how will it be affected? As you can see, as we calculated, we discussed and calculated, as you can see, it will definitely go down. That means it will decrease. Now 8.4.2, the reading on voltmeter V1. Okay, the reading on voltmeter V1. Okay, now we determine this, the power. When you calculate the power, it shows us the relationship between the resistance and the current, but we are yet to view the relationship between the resistance and the voltage. So what's what's the relationship? You said resistance is basically proportional to current, right? But I don't think that's not the same for voltage. If resistance goes up, what happens to the voltage? Up. So let's say voltage is equals to resistance times current. So you can see for voltage, what happens when the resistance increases? When this one, they are not against each other. So when it goes up as well. So that means when voltage increases, so does resistance. So when resistance increases, so does the voltage. So the reading on voltmeter we had 16,91, right? So let's now calculate it with changed value. So this is I equals to V over I don't know, I'm repeating it again. V is equals to our time is I, multiplied by I. Now our resistance, that's 4 plus 2 plus 3, that's 9. And let's take our 3,5. So that will be 9 times 3,5. Ooh, look at that. Well, we have so just as we predicted, 31,5 volts. So you can see compared to our former, voltage, which was 16.9 volts. You can see this is a huge increase. So you can already see what happens when resistance increases. So that means what will happen to the reading in voltmeter 1? It will definitely increase. And then they say explain the answer to question 8.4.2. We've already explained it. The current in the circuit, yes, it decreases, but what happens? The voltage increases. So if you want to explain it in a more formally manner, the way to write it in the book, you can say that obviously the total resistance of the circuit as explained will increase. So if we look at this, so let's do this. Okay, so this is 4 marks. So this is 4 marks. So that means 4 bullets at least. So now, the total resistance of the circuit will increase. The current in the circuit decreases. This is what we already deduced from 4.1 when we are calculating the power. This is what we already used. Now, that means the external already, that means the reading of voltmeter 1 increases because of what we've already explained as well. So that means also we can see that the resistance in the parallel branch will increase. So basically what you're getting is that because this is blocked, the resistance in the parallel circuit will increase because now it's series. It's in series, no longer in parallel because of this one is blocked. So it will increase. So once it increases, that means once this increases, the total will increase, the current will decrease, V1 will the same. So for instance, we've already explained as well. So yeah, I think that puts us to, yeah, this is the last question. So that puts us at our last question. So I hope guys we've learned from this, and I hope we took something. And I hope we'll continue with it. I hope we'll continue studying. I know it's especially for matriculants, you're gonna be almost at September, so try, and after that it will just be straight to your final. So you don't have that much time. So also grade 11s, grade 10s, physics, guys study. It's important to study. So once you see, the nicest thing about these questions is that once you do so many of them, it's easier to do the questions that even if you encounter new questions, it's easier to do them because you're already used to the style in which questions are being asked. Because sometimes it's not that you don't know the question or you don't know how to answer it, you know it, but it's just that the manner in which it's styled, sometimes you are unable to understand it. But once you do these questions, especially once you do a lot of them, you will realize that you get used to them, you get used to doing them, and once you get used to them, everything becomes easy. Even when you encounter a new question that you've never seen before, but you already know the style of the question, you'll be like, I know the style of this question, I know how this question is asked. So it's also important to just to go through the past question papers just to be sure. These questions, if you look at this question, if you look at other question papers, most questions, it's basically almost the same questions. It's nothing different. They might shift a little things around, do different things, instead omit the current and give you the internal resistance this time and ask you to calculate the current. But once you know your theory, once you know everything, it's easy to maneuver around them. So yes, on studying, and thank you for tuning in, and and I'll see you guys next time.